Today's topic is threads, and yesterday we talked about graphic user interface components, and that was a lot of programming detail and a lot of methods and a lot of different classes and stuff, but nothing really conceptually difficult or conceptually different than the stuff we did last week. Today is kind of exactly the opposite. There's mercifully very little programming and class technology. There's a little bit, but there's not a lot of detail associated with it at all, and the programming, to look at it, is pretty straightforward. On the other hand, it's a much more difficult concept to get your mind around, and it requires a lot of care in use. So let me start with a little background or motivation. Up to now, we've been writing programs that start from main and kind of execute along, calling methods and instantiating things and following a flow of execution, and essentially doing only one thing at a time. Okay? So it's easy to follow the flow of your code and see what's happening. Even when we're doing event-driven programming, where, from one point of view, the code is kind of popping into these event handlers when when it gets called from the Windows system, there's still really only one thing going on. Behind the scenes, your program is in that event loop, popping things off the event queue when they arrive, calling the event handlers, and then returning. Sometimes you want your program to be able to do two things at once, or three things at once, or multiple things at once. Okay? Some examples of this are, say, when we talked about stream I/O, we mentioned the fact that the read routine, the read method, could block. Okay? If you were waiting for some I/O on, say, the terminal, you could, or some network stream, you could do a read operation that would block. Now, say you wanted to be doing something else, say you didn't want your whole program to come to a halt there, say you wanted to be doing something else, you would, you kind of want your program to be doing two things at once then. Part of it is going to be waiting for this read to finish, whereas part of it's going to be doing some, you want to continue and do your processing. Another example is, say you have a program that really wants to be computing stuff, but nonetheless still wants to be responsive to all of your mouse clicks and keyboard events, responsive to the user interface. When I was talking about event handlers, I said that you should not put a lot of code in them, that they should be short and quick so that you can get back into that event loop and keep handling the events. But sometimes, you really do want to do some work. Say you have a big spreadsheet that needs to be updated, or some, huge computation on an image that the user requested. You don't want to do it in the event handler because, say, the user decides that, no, they didn't really want to do that, and they want to hit the cancel button, but, you've just queued up 10 minutes of computation and are not going to listen to that button click until it's done. Well, that's not a very good, satisfying experience for the user. So you would like to be able to do multiple things at once. You'd like to be able to still respond to the user interface while at the same time doing this image computation, letting that go forward. Another example is network downloads. This is similar to the blocking read case. Say you would like to download, instead of one file, multiple files simultaneously. For example, if you're a web browser, you get a page, you get all these links to the images in the page. You don't want to necessarily download the images sequentially. You might as well go and get them all at once. So you would like to start up your download loop multiple times and run them all in parallel. So the idea of threads is a mechanism to let you do multiple things at once in your program, to have multiple things going on. And it's hard to talk about threads without using the word threads. So I'm just going to say threads now. So think of that as threads of execution. Whenever you can trace through what your program is doing, either in a loop or a method call, following the program counter, think of that as one thread. And now think of your having a program where you can have two of these things going simultaneously. And that's the mechanism that we're going to talk about. Let's go for a little background first. I don't know whether the 6004 course talked about processes, but it's always good to refresh ourselves. So kind of the core notion that the operating system has of what a program is in Linux or whatever is a process. And a process pretty much maps onto the naive notion of program. And a good way to get a little more precise about it is to think about what is the state of a process. Okay, what information completely characterizes what's going on in your program at any given moment. And there's a lot of it. Well, not that much, but one thing you need is your the actual code. So you've got a big piece of memory. Okay, this is a big block of memory. And that's just the code for your program, all the machine instructions for your program. This is, to system programmers, usually known as the text segment. You then have another piece of memory, which is your program data. This is really kind of global data plus heap. Okay, in Java, since everything comes off of the heap, most of your data is going to be in this. So this is another big block of memory that's associated with your program. These are where all of your class instances live, all your instance variables live. They're all over here. What else do we have? We have another block of memory, which is our program stack, which is the sequence of the memory that's remembering the sequence of method calls we've made. Okay? The stuff on this is where the program stores the arguments when you pass them. It stores any local variables you have in methods. Okay? So if you do method foo, open curly bracket, int I, float j, I and j are going to be put on the stack. This is also where it passes return values. Okay? And so every time you do a method call, it puts a new one of these stack frames on and puts some more data. Every time you do a return, it pops one off. Okay? It's a very nice structure. There's also typically some piece of data that's usually stored in the processor called the stack pointer, or SP for short. All right, so that's another piece of information that is important to tell what your program is doing is where it is in the code, what instruction it's executing at any given moment. And that's stored in a special thing called the PC, or program counter. And this just has the address of the current instruction in this instruction code being executed. Okay? And this program data is all, has kind of pointers and links into itself, and the stack stuff has pointers into this data. This data should not have pointers back into, should not reference anything back in the stack, because the stack could go away when you do a return. What else do we have? We have a bunch of miscellaneous stuff. This is not really memory so much, but miscellaneous stuff. For example, any open files or streams you have, some fancy memory management stuff, none of which really has to concern us. I'm going to not draw a box around this, because it doesn't deserve a box. All right.
You mean resources and device context in general, or?
Pretty much all that stuff, anything that your program needs to run and has some state. So, for example, any open stream, any open device. And then there's a bunch of, as I say, stuff hidden from you. Memory management, which the operating system is using to make all this stuff work for you. So this is what your program looks like to the operating system. And this is just a really amazing concept, to store the state of a computation down to this level of detail. It allows you to do all sorts of stuff. If you've really captured the entire state of a process, as the operating system does, you can freeze it, take the state, copy it someplace, all right, and then sometime later copy the state back into memory in the processor, start it going again, and from the point of view of the program, nothing's happened, okay? It's like, you know, we were all suddenly frozen exactly in place, our brain molecules included, all of our molecules for 1,000 years, and then restarted again. We could never tell anything had changed, as long as everything around us went through the same process. This is how the operating system lets you run multiple programs and makes it look like they're all running simultaneously. You only have one processor in these machines, but nonetheless you can run Emacs and Java and, you know, your MP3 player and games and stuff all at the same time, and it all kind of works. And from the point of view of every program, they're the only program running on the machine, and from the point of view of the user, everything works nicely. And what's going on behind the scenes is there's a part of the operating system called the scheduler that loads a process into the CPU. This and this unit plus some of that stuff have to be loaded into the processor hardware. This and this and this have to be put in the computer memory if they're not already there. So it restores the process state for a given program, runs it for a certain amount of time, and then says either this process does a blocking read or a sleep or something that it doesn't have anything more to do, or the operating system just says, okay, you've run enough, I've run for enough time, I'm going to let somebody else run. It takes the state, it copies it someplace safe, takes another process's state, installs it, and then lets that process run for a while. So that's what's happening beyond the scenes, and the process involved in that is called scheduling. And there's a number of details about scheduling you need to keep in mind. The highest level detail of scheduling is probably whether you have what's called preemptive or non-preemptive. Preemptive scheduling means that the system is going to, at points at its choosing, usually regular time ticks, interrupt the process that's running, swap it out, and swap in a new one. So basically, process changes, process swaps happen unpredictably from the user's point of view. But everybody is guaranteed a slice of time. Okay, so the scheduler is going to interrupt whatever the program is doing, save it, let somebody else run. In non-preemptive scheduling, the scheduler is going to wait for the program to either go to sleep, call the sleep command, or to call, there's something like a sleep called yield, or do a blocking read or a blocking open, or do something that causes itself to be put to sleep. Okay, and only then is another program going to run. Okay, most operating systems at the process level these days are running preemptive scheduling. Certainly Linux is running preemptive scheduling. Otherwise, you would be able to lock up the whole system by putting, if you were running preemptive scheduling, you could lock up all of the programs by just putting your program in a loop that did while one or while true and then some random computation, which means that you would never go to sleep and never block. You would just eat up all the CPU, and since you had non-preemptive scheduling, your program would never be swapped out and no one else would get to run. And so that's why you don't like non-preemptive scheduling, although it does make some things easier, as we'll see. Okay, so keep those two ideas in mind. Another issue about scheduling is priorities. Some processes are more important than others, according to the operating system. So there are a variety of priority things you can set on processes, and higher priority processes will get more CPU time and will get kind of first crack at the CPU, and lower priority processes will sink down and run less often. And related to this is the idea of fairness and starvation. If you have a whole mess of processes of equal priority, okay, you would like, in some sense, a notion that the scheduler would be fair, that the whole set, each one would kind of get an equal amount of time on the processor. Okay, if they all had the same priority and they all wanted to do computation, they would all split the time allotted to them evenly. And again, operating systems generally will give you fair scheduling, but as we move on to threads, a lot of the assumptions that we take for granted from scheduling processes do not necessarily hold. So that's why it's good to keep all these issues in mind. All right, threads. Threads you can think of as essentially part of a process. In fact, it's this part of a process. Okay? Threads were invented because people did want to do two things at once, multiple things at once in their program. You can do that by splitting your program into multiple processes and then trying to get them to communicate via maybe shared memory in the data segment or message passing or whatever. Those techniques are difficult to program, and processes are fairly heavyweight objects. They take up a lot of computational resources. So you don't want to be, what's called forking processes all over the place. You don't want to make multiple processes because they are pretty expensive. Threads are much more lightweight, and so they're easier to do. They consist of like the basic structures of the stack pointer, the program counter, and the stack. So that's kind of conceptually what's unique to the thread. And if we think of a process now with two threads, say I duplicated that stuff over there on a different thread. Okay, so this is conceptually thread 2. We'll go back and label that guy 1. Now, we do have two threads of control executing in our program. We've got this PC who's reading instructions and executing them here, pushing and popping stuff off his stack, okay, doing his own procedure calls and returns. This guy over here, his program counter is on a totally different instruction. He's marching along, executing his instructions, doing his method calls and returns. Everything's working fine here. They are sharing the same program code, okay? So all the program code you wrote, they're both kind of marching around in there like little ants doing stuff. Furthermore, they're sharing the same global data and the same heap. Okay, this guy also has pointers down into the global data and heap. Okay, so this is cool. These are pretty easy to spawn. Spawn is the usual term for starting a new thread. So you can make as many of these as you need to do the multiple tasks you want to do, and they all run kind of independently in the program. Now, how do they decide to how do we do the equivalent of scheduling with threads? All right, and the question is, it depends. Some operating systems will support threads natively, and the thread scheduler is essentially the process scheduler in the operating system. All right. Some systems will not support threads natively in the operating system kernel, but have a kind of runtime library that runs at user level, which you can call into and will support threads or the illusion of threads or something like threads. And so you can get different effects in scheduling threads than the different rules for scheduling threads than for scheduling processes, even though it's basically the same procedure. It's implemented, it could be implemented in different ways. So we can get preemptive thread scheduling. We could get non-preemptive thread scheduling where one thread runs until it blocks or calls sleep or something. If you are running with a non-preemptive thread scheduling, you have to be very careful when you're writing your thread code to kind of share the wealth. So make sure that every thread, explicitly, make sure that every thread periodically sleeps for a millisecond or something to let other people swap in. Priority system, you can, again, it will give you a priority system on threads, so you can make some threads run higher priority than others. The implementation of this, I found, is uneven among systems. And that's, I think, the basic concept. Any questions? Yeah?
You said something about the runtime library sometimes handling threads. Is that if you have special thread needs or something, you would want to
No,
do
that's
that instead of what the operating system would do by default? Or?
well, you do that if the operating system by default doesn't give you threads, and you need threads. I believe that previous kernels of Linux and Unix did not have threads native in the operating system. So there's this pthread library that's floating around that gives you threads in Linux.
I remember hearing something about it not supporting green threads. I don't even know what green threads are.
Green threads are a Solaris native implementation of threads, I believe.
Okay, so that's totally different.
Java makes no commitment whether the scheduling is preemptive or non-preemptive. Okay? The Java spec says they're going to fall back on the whatever threading implementation is on the platform. And so if you want to write portable code, you have to take into account it could run under both scheduling conditions. And they advise that you assume non-preemptive, since if you have to assume the worst case of both. Okay, there's problems that this doesn't give you that this does give you, and problems that this doesn't give you that this gives you. Since you don't know, you have to account for all of the problems when you're writing the Java code. So, all right. So how do we make a thread in Java? And it turns out that this is pretty easy. It's very easy. There is a class or an interface. They give you two choices. The class is called thread, naturally. And to make to start a new thread of execution, or to essentially have a new main for this thread, you need to extend the thread class or implement this interface in a class. So one way to do this, as I said, let's see, we can do class what's a good name? Well, I forget how I did this in the example, but I'll call it walk. Extends thread. And the only interesting routine method in either the class thread or the interface called runnable is one called run. Okay, and I believe this is public void. All right, so you just do class, that whatever you want to call it, extends thread, and just put your code here. Okay, this run is going to be the equivalent of, roughly the equivalent of the main for your main program. You know, when you start a thread of execution, it needs to start someplace, so it's just going to start at run. And once you execute in run, you can call any methods on any classes you have access to. And this is just a normal class, so you could pass, you know, stuff into the constructor. You can set instance variables. You can do whatever you like. Okay. The other way to do this, if you don't want to, if, for example, walk is already going to inherit from something else, and you don't want to use the extends, you can implement an interface called Runnable. And Runnable just has one interesting routine on it that you have to override, or that you have to write, and that again is called run. All right? So you've defined these classes. They just define where the thread is going to start when you start it, but it doesn't start it yet. Okay? You've got to first do the normal thing of making an instance of a class. Okay, so say in your main routine or your main method or something, any place, you can do, let's see, let's do it this way.
What does the thread class give you that the runnable interface class?
Nothing really. The, I guess, benefit for doing it this way is that you can have Q inherit from some other things, as opposed to doing it this way. But they're roughly equivalent. And as we'll see, in both cases, we do have a thread class running around. So in one case, we can do.
So why don't you just have the runnable interface? Forget about the thread.
Oh, well, as you'll see, the thread class comes into it in both cases. And whether you extend it or implement runnable and then use it is, I guess, just a convenience for the user. But to run this thing, thread T1 equals, okay, if we've inherited, we can just do a new walk. Okay, and let's get another one. Thread T2 equals, now we always need a thread, so we're going to allocate a thread, instantiate a thread, and what we're going to give it in the constructor, here I'm using a null constructor, I'm going to give it one of those. So I've got to make a chew. I apologize for overriding this. Maybe it will be clearer if I get rid of this. This is in the notes. All right, so I make one of these chew objects, which implements runnable, and then I feed that as the argument to the constructor of thread. So both of these things, at some level, are threads. This one, I've made a thread directly. This one, I've made a walk, but walk, if we remember, inherits from thread. Okay, so now I've created them, but they don't start running even yet. I just have these thread objects, which I can do various communication things to. And I could pass other data into this one, or into my chew if I wanted to have instance variables to initialize. Okay, that's where I would pass them in. Or I can do normal accessor and mutator methods on instance variables on these. These are both regular classes. Just and to get them going, the basic command is start. Okay, when you issue, call the method start, t2.start. That says it makes a new thread, one of these under the covers, and starts it running at the run routine, the run method of your class. So it just starts going. And then it continues to go essentially until this routine, either this routine returns or somebody outside kills it. There are ways to, once you have a handle on a thread, to kill the thread from the outside, or you hit the system exit, which will kill all of the threads. So I have an example of that over here, just to show you an Emacs. I guess I did it the opposite in here. I have chew extending threads, and my run routine here is just going to go into a while true loop that runs forever, and it's going to print out chew, and then it's going to go to sleep for a random number of milliseconds, up to a second. And you have to put this in a try-catch loop because sleep will whine if you don't catch its exceptions. Same thing here for my walk class in this case. I'm implementing runnable. Again, I just define a run routine, and this one goes into a while forever loop, and it prints out left, then it sleeps, and it prints out right, and it sleeps. And yikes. Okay. And then my main is just making one of these. I just can instantiate the one I inherit from, and the one I don't inherit from, the one that implements runnable, I have to pass in as into the constructor of thread, and then I just start them both. So if we, I guess I have just compiled this guy. If we look at what it does, okay, it just prints out left, chew, right, okay, and notice that they don't come out in any particular order. It's pretty random, given the thing is just printed out a chew, whether it's going to print out a left or a right or another chew on the next thing it's going to do. Now, some of that randomness is imposed by my random sleeps. I just put those in to slow it down. If I took out the sleeps, you would see the scheduler run one of them for a while, then swap and run the other one, and swap and run the other one. So you'd see a whole mess of chews, then you'd see a bunch of left, right, left, right, left, right, then a whole mess of chews back and forth. And but the points at which they switch, you have no control over what's going on. Okay, they're going to swap at random places. It does appear that these threads are preemptive scheduling, because I can put both of these in while true loops, and both of them will get to run. So, but you can't count on that if you're trying to write portable programs.
Is the sleep function sleeping for a specific amount of time that thread would get, or is that actual sort of grand time?
Yeah, that's supposed to be grand time. That's supposed to be real clock time. It's not going to be totally precise, but because of that scheduling issue, but it's basically going to stop being runnable for that amount of time and then try and run again.
But I don't understand why that's necessary. Why is that preemptive, just based on that?
You can't tell based on this, because indeed they are printing things. And as a matter of fact, even my previous experiment, I would have to say, is not conclusive. So I guess I'll backpedal and say I don't know. Because if you think about it, it's very hard to do an experiment that tells, because at some point you want to get an answer out of the things, but you can't have them, you can't do any system.out.printlns in the loop, because that potentially will cause a yield. Okay, anything that calls an I/O function is potentially going to cause the thread to yield, and even in non-preemptive scheduling. So what I would have to do is write one loop that increments some variable up to, increments a shared variable. We'll have them both increment different variables, I guess, and then have a third thread that kind of monitors them and prints out that condition periodically and see if, if one of them was incremented all the time or the other. It's pretty tricky to show. But the bottom line, I guess, is that since you don't know, you have to plan for the worst case. Right, so that's going back to our issue of fairness and whether the underlying thread implementation is fair. My experience in other contexts with Linux pthreads, and I don't know what version this is using or what it's depending on, but in other contexts, I found that that pthreads do not tend to be fairly scheduled. And again, I couldn't say for sure whether they're preemptive or not. I have found that Microsoft Windows threads are amazingly fairly scheduled. I've run experiments where you spawn 24 threads, set them on a compute task, and count how many times they've completed it, come back the next morning, let it run overnight, come back the next morning, and they're all within a few percent of how well they've done. So kudos for them for doing an excellent job.
If you took away the sleep statement,
Yeah.
you wouldn't it be so that, well, what would happen then? I guess it would depend on.
Yeah, it would do pretty much the same thing, but faster and in bunches. So you'd get a lot of chews, and then it would swap. And as each one of these things gets to run its time slice, well, we can try it and see. It's a pretty easy experiment. First, we should get rid of that. Come back here. Get rid of that. Get rid of that. Oops, not that one. Get rid of that. Get rid of that. Nope. It'd probably whine if I have an empty try block. So.
In the second one, you get rid of your try block. You get rid of your
Oh. It is kind of whiny, isn't it? Okay, so now you can see it do scads of one, then scads of the other. And it's harder to see at what point it's switching, but it's probably switching in fairly randomly from any test you can do. So
But if it was non-preemptive, wouldn't it just print the walk?
it would, except that we're doing these system.out.printlns, which probably give do some kind of thing that would yield inside. Okay, so once you call any of these system functions, you're really not you're jumping into the system, which is going to give it a chance to run the threads. So I suspect it's preemptive, but I have no conclusive experiment. Yes.
If we call the yield method on the threads, then would you say that allows threads to be more polite?
Yes. Yield is equivalent to sleep for no time. Okay, it's kind of a sleep of zero.
Perhaps alternate?
No, they would probably do something similar to this, because even if they were, just because you yield doesn't mean you have to yield. It's just, I think that the system will tend to allow it to run its time slice if it's too often. But the moral of the story is, once you have two things going on, you lose all track or in control, okay, especially if you have preemptive scheduling, of what's going on when, okay? So each one of them could be anywhere in their process unless you explicitly synchronize them, which is our next topic. Except, well, I'll just refer you to the documentation for other things you can call on threads. You can do various things like various types of signaling, like kill threads. If you have a hold of a thread's object handle, you can kill it, you can tell it to, you can block it externally, you can wake it up, you can do all sorts of things. You can wait for another thread to wake you up. You can do all sorts of sophisticated communication, which we're not going to talk about, but feel free to use. But the next issue I want to talk about is thread synchronization, which addresses the following problem. I guess I'll just use this, since that's up in the Emacs. Say we have some lame piece of code here. Now, we said that these threads can share data. Okay, if they both happen to have a reference to the same object in memory, they're sharing it. And if they are both kind of accessing it and reading and writing it, you have to be very careful, because you have no idea in what order these things are going to happen. For example, you can take a perfectly innocuous statement where, like, A equals A plus 1, and say there's two threads that are sharing A and are both executing this code. And say A externally had been initialized to say it somehow got initialized to 3. But both these guys are executing this code. Now, if you think about how this is broken down in the machine, what's happening is the processor has to go get A, okay? Then it has to, in its guts, it has to increment A, and then it has to write the new incremented A back out to memory. All right? Now, if we have two processes or two threads doing this at the same time on the same variable, they can do those two steps in all sorts of different interleaved orders. Okay? The order that's happy is that thread 1 reads A, thread 1 increments A, thread 1 writes A back out. Okay? And then thread 2 reads and increments A, and then thread 2 writes A back out. Okay? That gives you kind of the behavior that you'd expect if, you know, both threads go through and execute this guy once. You would expect A to be incremented by 2. Okay? Because you have two threads, each of which are incrementing A by 1. Now, what can go wrong is if they happen to swap in the middle. So thread 1 goes and reads and increments A. So internally, it's thinking A is 4, but it hasn't written it yet. Then thread 2 comes along and reads and increments A. So internally in its data, it's got A equals 4. Okay? And then thread 1 goes and writes A. So it's set A to 4. And then thread 2 writes A, and A is set to 4. So in one case, things can be arranged such that A comes out 5 at the end of both of these going through once. Okay? In another order of execution, which we have no control over, it comes out 4. Now, sometimes you might not care whether you get the same answer in your program all the time, depending on how it's scheduled. But most of the time, you do. Most of the time, you would like your computation to be deterministic, that no matter what the scheduler is doing, you know, you get the same answer out. You get a valid answer out of the computation. So this brings up the whole issue of thread synchronization. Which is hard to spell. And the basic problem we're trying to solve is to restrict the order of execution in these shared data so that one guy gets in, does the entire job of reading, incrementing, writing, and then leaves, and then another guy gets in, does the whole job of reading, incrementing, writing. So we always get valid increments. We don't get these half increments that don't go anywhere. Now, there's a pile of mechanisms for doing this that people have developed, programming paradigms. One is called critical sections. It's spelled wrong in an early version of the notes. Critical sections. There's something called mutexes. There's something called semaphores. There's something called monitors, which I'm less familiar with. But the basic idea of all of these things are the same, that you lock that a thread can lock deterministically a section of code, in this case, or a combination of code, get a piece of data which can then be used to leverage locking code. Semaphores are a more sophisticated version of mutexes, which have counting properties. But the basic idea is you want to lock that section of code so only one guy can get in there at a time. Only one thread can execute at a time. Yes?
Aren't some of these for between process synchronization as opposed to between thread synchronization?
The underlying mechanism can probably be used for both. Critical section, since it really locks pieces of code, probably doesn't make much sense between processes because this, that's not shared. But these can be used for threads or for processes. And the implementation of all of these, the underlying bottom level implementation of them requires operating system intervention. It turns out if there is no way to do this, if you don't have any of these, there's no way to build synchronization at the user level because you don't have any control over that synchronization. And any scheme you come up with to do some locking is going to have a loophole in it that if the scheduling fails or happens in just the right way, then your scheme is going to fail. Okay? One of the things that's fun to do is come up with various locking schemes and see how they fail. Underlying the basic operation you have to be able to do is an atomic test and set. That means you have to essentially be able to look at a piece of memory, test whether it's equal to 0, and set it to something else, all without any other process or thread getting at that piece of memory. And once you can do that, you can essentially bootstrap that up to build any of these things. Yeah?
So do threads most of the time do threads share the same data, or are they accessing completely different? I mean,
usually they share a small set of data because they have to communicate and interact somehow. Otherwise, if a thread is going off and being completely on its own, it's not doing very much, then
so like in this case, what?
In this case, they're not actually sharing any data. But on the other hand, they're not doing anything particularly useful either.
Okay.
So usually there'll be a very small amount of data that the threads will share. For example, if you're downloading multiple images in a browser or something, all of the mechanism for downloading the images would probably be separate. But finally, all the images have to combine into a page, right, a display, and that's probably where they're shared.
I read an ad system for the New York Times, and the threading issue was really critical in keeping track of how many ads were presented, like these totals, because we'd be delivering thousands of ads a second potentially, and the simple number of how many we've been served, just maintaining that, like, causes massive semaphore problems, like blocks on loop. And
Was this a web system, or was this a? Yeah, you run into this stuff enormously when you're writing web server applications, because in a lot of web server applications, all of the different people who you are serving, okay, all of these requests that are coming in from the internet are all running in the same process and sharing a bunch of data, and then there's potentially thousands of these guys simultaneously, and anything they share, as we'll see when we talk about Java servlets, yeah, it can just be, you got to be really careful and do it right. Plus, these things are expensive. And they're expensive for the following reason. If you think about it, we said we want to lock this section of code so only one guy can get in there, only one thread. So say two guys try to get in there. Okay, what happens to the other guy? Well, the systems say they try and get in at the same time. Whatever mechanism is implementing these things is going to decide a winner and a loser. The winner is the one who gets to execute the code. So he just goes through and executes the code. What happens to the loser? Well, the loser essentially gets stuck right before the critical section, or the mutex that they're trying to grab. And he just waits there. He's essentially put to sleep until that resource is freed up. Okay? And so he locks up. So if the other guy is taking a long time, or if there's a lot of people queued up waiting for this resource and one guy is taking a long time, your threads are going to stop doing work because they're all waiting for this resource. All right. So, but you have to do it. So you want to make anything that you lock, you want to make it as small as possible. All right. So you just want to have the locking thing be very brief. Whatever data interchange you're doing, you want to be able to get in there, lock something, do it, and get out, which is what makes a lot of this challenging. Yes?
Is there a way to partially pre-up things? For example, say two things are trying to get to one point, but the one who gets there first needs something that the other guy was going to release.
Right.
And the other guys can't release anything until he gets.
Right. We'll talk about multiple resources in a second. That's where things get even more complicated. But yes?
What about determining, like, if two threads request something at the same time? Is that
Yes.
an issue, determining who's first?
The threading implementation, whoever implements the synchronization mechanism is guaranteeing you that they're going to choose somebody. It might be an arbitrary choice, but only one guy will win, which is a very difficult thing to do and propagates way down into the electronics, trying to solve that issue. Did you talk about that in the 6004 thing at length? So the metastable problem and all that sort of thing. Okay. So let's talk about how to do this in Java. Java really doesn't directly implement these. It has a mechanism. I'm going to erase this. Say we have a class with our variable A and our public void increment. Okay, this is the thing we want to protect. It gives us a keyword, synchronized, which we can add to methods. Okay, this is a keyword that goes on methods, not classes. And what this does is it allows only one thread to execute this method at any given time. Actually, it does more than that. What it does is it locks this entire class, the entire instance, not all the instance of a class, but if I call increment, if I make an instance of my class, and I have all my threads calling increment, anytime a thread gets in here, it will lock that entire instance such that not only will any other thread be able to start this synchronized method, they will not be able to get access to any other synchronized method on that instance. Okay, so it's not quite it's a little more powerful than a critical section because it's not just locking you out of this piece of code. It's protecting the whole instance, but kind of in a limited way. If you have non-synchronized methods on the class, those will still run. So anybody can use a non-synchronized method, even if somebody's in a synchronized method. But a synchronized method, once somebody's in a synchronized method, then all threads are locked out of all synchronized methods on the same instance. So usually you would only have, you would wrap these around your critical sections. And again, all the threads, once somebody is in here, or in a synchronized method on a class, all the other people who want to use those synchronized methods, they just queue up. They're put in a wait state, and they build up. And then when you exit the critical section, the system will find somebody. If there's anybody queued up waiting for it, it'll pick somebody off of the queue, and they'll get to enter and run. Yeah?
When you say it would all be locked out of all synchronized methods
on that
in the
instance.
same instance.
Right.
My class is, so you're saying that my class is an instance of a class, that there are threads manipulating or using methods in that class?
Right. I would say that what you would do is say, my class foo equals new my class to get an instance.
Right.
And say you did another one, which was bar. All right, so we have two my classes, foo and bar, and then everybody was calling foo.inc. Okay, essentially only one thread at a time would get into foo.inc, but even if this somebody was in here, another thread could get into bar.inc, okay, without causing any trouble. So each one of these is synchronized independently, foo and bar.
And then these synchronized methods are completely independent in their declaration of the thread classes. They have nothing
Right,
to do with
right,
it.
right,
Okay.
right, right. So all it means is at some point, it means that the system has to put one of these mechanisms around it. So use them sparingly because they're going to be expensive. They're not only going to have the possibility of people waiting on you, but they are a little bit overhead. So some things interesting to know about the Java system is that we have all these utility classes that it gives us, and some of them are synchronized and some of them aren't. Okay, so when you use them, if you're using them in a multi-threaded system, you have to know which are which. Yes?
I imagine the system's smart enough that if it's a recursive method, the method that is in there gets to continue to call it?
Yes, yes. I should have pointed that out, that once a thread has locked an object, it can use multiple synchronized methods. Threads do not block on themselves. So all of that kind of works. One thing you don't have to worry about in Java, because it takes care of it for you, that you would have to worry about in other implementations, more explicit implementations, is say this method didn't, say you lock something and the critical section or you were trying to execute didn't complete normally, but threw an exception. Okay, so if you do a lock, you call some method, you throw an exception which unwinds your stack. In Java, I believe that will release your synchronization, but in other languages and other systems, it won't. So you have to be very careful if you're using, say, mutexes in C, that all paths out of the locked thing, whether it's an exception, whether it's return, whether it's, you have multiple ifs out of this section, multiple branches, you have to make sure you unlock all of your resources as you're leaving. Yeah.
Sorry. Is there any way to independently synchronize methods on an instance?
Independently synchronize.
Because all synchronized methods are locked on this instance.
Right.
I can't call deck, since deck is also a synchronized method
Yes.
from another thread. And I want to.
Right. The conceptually easiest thing to do is probably to make two instances. But what you would have to do is you basically use this mechanism to build up your own mechanism. So you would have you would like to be able to make inc and dec run. That doesn't, since they share data, that wouldn't. Right, but say there were two, say there was an A and B, and you had an inc A and an inc B. What you would do is make one of these guys that was synchronized that would say, you'd have a lock A or lock B thing. Okay, so that would go in and lock just the resource you want, all right? And then you would have to write your own thing on each one of those things to test to see if the lock okay, and do your own weight. So basically, once you have this capability to set some lock, okay, you can basically duplicate some of this functionality by hand, and it's stable and it'll work.
So you'd have like an inner class that had synchronized methods or something like that for the data.
Well, I guess what I would do is for everything, if everything independently you want to lock in a class. Okay, it's a little bit beyond our scope. I would build by hand a mutex, okay, and I would use the synchronized method only to set the mutex, not to guard the algorithm that uses the data, and then basically use that scheme. So you go in, you grab the mutex, and because you're doing that synchronized, you can make that work stable, and there'll be no collisions in the threads. Then you go off and you use that resource that you've mutexed, and then you can release it. Okay, and all you need to do is put the lock and unlock routines for each mutex being synchronized. Okay, so that's how you can kind of bootstrap. Once you have a basic locking mechanism, you can bootstrap any of the others. Yeah.
If, when you drop into a synchronized method, it locks the synchronized inherited methods also, right?
Yes.
What if the process goes into a synchronized method,
Mm-hmm.
you know, and then another process tries to go into a synchronized method that is one that's being inherited?
Since it's done on an instance by instance level, it's the instance itself that's going to be locked. So it would all work. It would all work right. Basically, the object would be locked for all of the guys synchronized. I don't think there's any hidden dangers there.
Even though the child process couldn't lock it, it would be all right?
If I guess the rule I would say is if the child process couldn't get in, or if any thread couldn't get in by having the lowest level handle on the inheritance chain, it wouldn't be able to get in having any higher level channel, or vice versa, since the instance remembers what it is and all of its method types. Okay, one last topic which somebody brought up, which we have to watch out for when we're using synchronized methods or any locking mechanism, is deadlock. Okay, and this happens when you have processes that want to call a synchronized method on one class, and then, or one instance, and then inside that go and call a synchronized method on another instance. Okay, so what it's essentially doing is locking one instance, one object, and then it's going ahead and trying to lock another instance. And so the problem comes up is what happens if somebody else has locked the second instance? He has to wait. Okay. Now what happens if you are so unlucky if the guy who has locked the second instance is waiting for you to give up the first instance? Okay. So if you have process thread A, T1 doing lock A, lock B, and thread 2 doing lock B, lock A, okay? If both of them get to this point in synchrony, okay, now T1 is trying to lock B, but T2 has it, so he's blocked. And this guy is trying to lock A, but T1 has it, and this guy's blocked. And so you're stuck, and it just stays that way forever. Okay, that's why it's called deadlock, or occasionally the deadly embrace. There are many, many instances of this. I mean, this is a very general and broad problem having to do with people or systems trying to grab and lock shared resources, especially multiple shared resources. This is why it's a huge fine in Manhattan to ever stop your car in the middle of the intersection box, okay? Because you can easily get into deadlocks there, since in order to get out of your intersection box, if you're in it, somebody else has to free up the intersection down the street. But if they're blocked waiting for the guy below them, and they're blocked waiting for the guy over here, and he's blocked waiting for you, the whole thing just jams up in a square that there's no way out of. So you can, this deadlocking issue comes up in all sorts of cases, and there's a couple ways out of it. One of which is you could say every time you hold something, if you end up blocking on somebody, you could always time out periodically and release all of the things that you have, kind of back out of your locking process. That can be inconvenient if there's a lot of code in between here and here, you've got to undo all of that code and get back to the point where you can release this so you can start again. Or you can be smart and make that easier. So first you go through a phase where you try and allocate all your resources at once, and if any of them fail, you kind of time out and release them. And that gives you kind of this random phase, this random behavior where if you can't proceed, you release everything, and everybody's doing this, and eventually somebody will get lucky and get everything they need and continue, and vice versa. I mentioned in the notes probably the dining philosopher problem, which is an interesting way to think about these things. You have the 5 philosophers, and they're all sitting in front of plates of pasta. And in between each one of them is a fork. And each philosopher needs 2 forks to eat the pasta. All right, so you try and think of algorithms for, this is a test for various synchronization and resource allocation algorithms. You can think of an algorithm where, everybody grabs the fork to their left first, and then tries to grab the fork to their right, okay, and then eats and then puts them down. Of course, that doesn't work because everybody just grabs, if they're all in synchrony, everybody grabs the fork to their left and is waiting for the person there. So you could randomly have some people go left, some people go right, but topologically, that's not going to work either. It'll proceed for a while, but eventually there'll be people blocked, and you'll end up with a chain. You could have the scheme I described where you back out, says you pick up the fork on your left, you try for the fork on your right. If you can't get it, you put it down. So that involves a lot of people doing this, and eventually somebody will get 2. But it's kind of uneven, but it's nonetheless doable. The most reliable scheme is if you have a system where you can globally sort all of the resources that anybody's going to lock, okay, you can develop a stable system. Okay, if you know the entire set of instances that can be locked, okay, and you can put a ordering on them, then everybody can take the rule that they will lock them in increasing order. So say A is before B in the order, that means this attempt would be disallowed, and anybody who needs both A and B to do anything will always ask for A first, then B. So T2 would have to lock A and then lock B. And then there's no problem because they compete for A. One guy wins. That guy is guaranteed to get B because no one's locked it. No one could have locked it. And will return to finish, and then this guy will complete. And if you do the sorts, no matter what subset of the locks people want, somebody will always be able to get the set of resources they need to complete. And then once they complete, everybody will unwind behind them. Okay, so it's a reliable way to avoid deadlocks. It does require a global ordering of all the things that you want to synchronize. Yes?
Will it pipeline? So once it's in lock B, will T2 go into lock A?
That's a scheduling issue, really. It depends on how fast these processes go and what the scheduler is doing and what else is going on. So it could potentially, but it's not guaranteed to. So now, all of this locking stuff is only a problem really with preemptive scheduling because we don't know when the processes, the threads, are going to be swapped. If we had non-preemptive scheduling, that means we never would switch threads until we explicitly said yield or called an I/O routine or sleep. Then all these problems go away since all these things are just manipulating data. The thread, you're sure the thread is never going to be swapped in there. So if you know you have non-preemptive scheduling, it makes the synchronization much easier. But on the other hand, it makes the fairness issues a lot harder because you've got to yourself do all the work to make sure every thread gets to run and the whole thing works smoothly. So in Java, as I said, you don't know which you have, so you have to account for the worst of both worlds. You have to put in sleeps and yields to make sure that if you have non-preemptive scheduling, all threads will get a chance to run. But nonetheless, you then have to synchronize everything explicitly that needs to be synchronized in case you have preemptive scheduling, and so you would run into these problems. I guess that's all I have to say about threads. Any questions?
Do they work in Java? Are they really
Oh yeah, that was. Oh.
But are they really stable? Can you count on it?
The synchronization works, yes. And as far as I know, the implementation is sound. Oh, what I was saying about the utility classes. Swing is not synchronized. So if you are running a multi-thread system, don't send multiple threads into Swing. Only designate one thread to be your display thread or the thing that's interacting with Swing, and stick to that. A lot of the container classes are not synchronized. The newer container classes are not synchronized, so you have to be careful using them with multiple threads. The older container classes, which would be vector and hash table, are synchronized, but consequently more expensive to use. So, so be aware. The project will, I think, require several threads for a good implementation for problem set 3. So.